Hi, I'm Travis English, and this is Air Considerations in Imaging or X-ray Rooms. These are the learning objectives. If you'd like to read those, press pause. Moving on in 3, 2, 1. Okay, so the Class 1 imaging room, which used to be called the X-ray Diagnostic and Treatment Room, is a pretty common space in healthcare. And we're going to look at those spaces and the air requirements in them. We'll look at the ASHRAE standard requirements, both historical and today, including the recent changes. And we're going to talk about infectious aerosol risk. And then we're going to look at cooling loads. And based on all this, I hope to convince you that the ASHRAE standard prescriptions that we don't have, or that we have right now, don't make a whole lot of sense based on the varieties of these spaces. And I'll urge you to use the newest standard, which really provides the most design flexibility. Okay, so in October 2019, ASHRAE Standard 170 changed the name of X-ray Diagnostic and Treatment, which was the previous name, to Class 1 Imaging Room. And at the same time, we added these definitions. Class 1 Imaging Room is diagnostic radiography, fluoroscopy, mammography, computer topography, ultrasound, MRI, nuclear med, and other imaging modalities, including services that use natural orifice entries and do not penetrate any natural protective membranes. So basically, this is any type of imaging where we're not significantly cutting into you. I remember I once had an infection control person tell me, if we go into your body through a hole that you already own, that's not invasive. So this is all non-invasive imaging, although needles are allowed. The Class 2 and Class 3 imaging definitions ramp up to more invasive procedures. But today we're just talking about these Class 1 spaces, the sort of running horse of the imaging spaces. Okay, so let's look at the historical requirements. This table shows the historical outdoor air and total air requirements in air changes per hour for X-ray rooms. From the inception of the table, by the way, until 2019, that space was called X-ray Diagnostic and Treatment, the way that you see it there with the quotation mark in the right place. Then just 2 years ago is when we changed it to Class 1 imaging. So starting off in the early 60s, it was 6 air changes. Then in 1966, we changed it to 10 air changes for 1 code cycle. And the reason we did that is because that was the one time that George Lazenby played James Bond. And then... I'm kidding about that, totally kidding about that. It used to require, in the 60s, used to require 100% outside air. In 1978, we dropped the outside air down to 2 air changes, but we kept the total at 6. So throughout the 90s and early 2000s, FGI actually only published the total ventilation rate, not the outside air rate. And then ASHRAE picked it up in the Daniel Craig era, and we started publishing the rates then. 6 air changes and 2 air changes all the way until the current version, which we're going to talk about in just a second. So first, let's talk about the evidence basis of the requirements. You may be wondering, what is 6 air changes per hour or 2 air changes per hour based on? Like, where do these numbers come from? Well, ASHRAE did a research project to answer exactly that question. It's called Project CORP02, evaluating the scientific evidence behind Standard 170. So in their final report, they published all of the requirements in the standard. You see those in columns here. And for each one, they said, can this be justified based on rational inclusion? In this case, no. Can it be justified based on a clinical practice or a clinical source or a clinical need? In this case, no. Is there any available evidence to support the requirement? And in this case, no. So for imaging rooms, there's no rational, clinical, or evidence basis for any of the requirements. The reason that we use them today or up until a year ago is mostly because we've been using them, since before I was born. My opinion, that's not a super good basis for an engineering standard. All right, so let's look at the current requirements. The current standard addresses Class 1 imaging actually in 3 different locations in the standard. You have Table 7-1 for inpatient spaces, and then Table 8-1 for specialty outpatient spaces, and then Table 8-2 for general outpatient spaces. And right away, I'm going to argue that this makes 0 sense. Imaging rooms are never inpatient spaces. Nobody ever stays there. And by the definition of Class 1 imaging, they are not specialty outpatient spaces. Class 1 is, in fact, the general and non-invasive application. So the first two tables here, 7-1 and 8-1, really don't make any sense. And so I'm going to urge you right away to focus your attention mostly on table 8-2. When we look at all of this in terms of outside air requirements, outside air and total air is what we're going to look at. The outside air requirement, 2 air changes per hour, is common to 7-1, 8-1, and the first method in table 8-2. 8-2 being the one that you're likely to use, or that I would urge you to use. But in 8-2, there's actually 2 ways of calculating outdoor air. You can calculate it based on 2 air changes per hour, or you can calculate it based on 7.5 CFM per person, 0.12 CFM per square foot under the so-called RARP method, which I'll show you later. That's what I recommend that you use. In terms of total air changes, 6 air changes per hour of total air is common to the first 2 tables. But then in table 8-2, the one that you're likely to be using, it is 3 air changes per hour under method 1. Under method 2, there's actually no total air change per hour requirement. But if you look at the text, it says that you need to use at least 1.5 times whatever you've calculated as the minimum outdoor air. Obviously, that's the lowest requirement. That's the one that I'm going to urge you to use in most of these applications, right? Okay. And here's the big sort of problem and crux of this. There are a bunch of spaces that fall into the category of class 1 imaging. And here's a list of them. I happen to work for a healthcare owner, so we have templates for each one of these rooms, and they range from 140 square foot up to 540 square foot. And there's no standard ceiling height. Some of the MRI rooms and CT rooms do have high ceilings, which means that the volume can vary quite a bit for each room. The size of the rooms varies quite a bit. The volume of the room varies potentially even more. So for all of these rooms, each of which has 2 people in the room, for about a 20-minute period with a piece of imaging equipment, our outside air calculation varies by a factor of 4, and our total air calculation varies by a factor of 9. Now, if you ignore the inpatient and the specialty outpatient tables, so you leave aside the 2 air changes per hour and 6 air changes per hour thing, and use these new numbers, the RARP method, then the variance is quite a bit lower. The variance comes down to about a factor of 3. But even then, there's still quite a variance, right? Factor of 3 variance on what you're going to do. All right, so let's move to infection risk. The most simplistic consideration of infection risk, we can use the Wells-Riley model. There's about 1 million disclaimers that go along with this. And by the way, this presentation does accompany a white paper. So if you want to read all those, please do. They're in the white paper version of this. But a class 1 imaging space is going to be this first column that we have on the left here, a 20-minute exposure time. And for a disease with an aerosol generation rate similar to COVID, SARS-CoV, we need to see about 37 CFM to maintain a 10% environmental aerosol risk in that space. A 1% environmental aerosol risk in the space happens at about 390 CFM, 380, 390 CFM, which also, by the way, corresponds to a 10% risk occurrence for a disease like the measles. The measles is roughly 10 times more virulent than COVID or SARS. And so if you wanted to go to kind of the idea of a 1% risk for the measles, then you would need quite a lot of air, like 4,000 CFM. That's not practical in any of these rooms. Even the large rooms, that's not a practical amount of air. So really, I think what we should be targeting here is targeting that 10% rate for the SARS and having at least about 37 CFM. We're going to call that 40 CFM in the room. There's very few of these rooms that we would run with 400 CFM as a minimum all the time. To make sure we pointed out, any infectious aerosol risk model that you do is always going to be based on a number of people. There's going to be a ventilation rate in CFM and a number of people. So CFM per person or CFM per infectious aerosol source is the right way to think about infectious aerosol risk, which is to say that an air change per hour metric is ill-suited to the idea of infectious risk. right? Infectious risk has absolutely nothing to do with the size of the room or the volume of the room. Another thing that's worth noting is that the room environmental aerosol risk is a function of the total ventilation of the room, not just the outside air. Every CFM counts. Every CFM that you bring into the room acts to dilute those infectious aerosols. So if we take this 37 CFM number and remap that, and the 370 CFM number, and we remap that back onto the standard aerosol requirements, you can kind of see that where we stand. For any of the spaces that we're doing, we're always going to meet that 10% risk threshold. Very few of these spaces, in fact, only the two largest spaces would ever meet that higher threshold. So unless we're planning on jacking up our ventilation standard quite a bit, I think we should accept that, you know, this roughly 40 CFM level as a minimum is probably the right place, and that's where we're at in all cases. So now let's move on to cooling loads, because the ventilation, the other thing that the ventilation in these rooms needs to do is to meet the needs of the cooling load. I don't believe that our standard ventilation rates are supposed to accommodate cooling loads, but we're going to have the conversation about cooling loads anyway. We had a 2009 ASHRAE research project by Dan Koengsfer to put together data on peak loads and standby loads. And so this is the sort of results table out of that research project. I believe this is also what you'll find in the ASHRAE handbook at this point. I want to point out the magnitude of these numbers. For MRIs, we're looking at hourly peaks, a 1 hour peak of 80 to 85,000 BTU, standby at 70,000 BTU. Linear accelerators are even higher. The CT scanners and CyberKnife numbers are around 45,000 BTU peak and 35,000 BTU idle. Those are pretty big numbers. So what I want to show you now is an example from the actual built environment. So another way to look at cooling loads is to back check them based on historical data. So this is a set of rooms in one of our relatively new facilities, and we pulled trends for the airflow, the room temperature, and the supply air temperature at 5-minute intervals for about 45 days. This graphic is showing 1 week of that data. And the short version of this is that the historical loads, the historical data in the room shows that the loads are a whole lot less. It is very rare to see a load that's over a half ton. It happens, you see those X's that are up there and those squares that are up there. But so it does happen. You do get loads that are up towards 2 tons, or at least 1.5 tons. But when you do, it's not a 1 hour peak. It's more like a 5-minute peak that resolves in the next period. The average loads in the room are very low. In fact, they're that low, right? About 2,000 BTU is a good number to think about there. We've been doing some data analytics on other imaging spaces, and this is pretty consistent. The average running load, even in the rooms with the biggest pieces of equipment, is very low. It's basically, you know, it's not very much at all. There are peaks that occur, but those peaks are actually really brief. So from a temperature control perspective, we probably want systems that are able to accommodate those peaks, though they are very short-lived peaks. But we want to make sure that we can turn down, and we should be able to turn down to a very low or no load condition. Probably want to be able to turn down to 100 CFM or half that, maybe 50 CFM. Let's bring this all together. Any class 1 imaging space is basically 2 people in a room for 20 minutes with a piece of imaging equipment. The size of that room is going to vary by a lot because of the different types of equipment, and different types of equipment require different sizes of room. That doesn't matter to the HVAC system because it's always going to be 2 people in the room for 20 minutes. Aerosol risk is something to think about, but that is also not related to the size or the volume of the room. Occupants are the sources of infectious aerosols, and in these spaces, we'd always be talking about 2 people. So that number is about the same. We saw that for a disease like COVID, the environmental risk is held down below 10% when we use a room ventilation rate that's over 37 CFM or 40 CFM. For the biggest equipment, the MRI machines, the actual running load is probably going to take, you know, 100 CFM or less. I think we should actually include turn down to about 50 CFM, even for the large MRI machines. So the cooling loads are going to be short, intermittent peaks, and most of the time there's going to be very little load in the space. And so do we need 6 air changes per hour in these rooms? I don't think so. I don't think we ever need 6 air changes per hour in these rooms. Do we need 3 air changes per hour in these rooms? No, probably not. We definitely I wouldn't design a minimum at 3 air changes per hour or even 2 air changes per hour. I think the correct way to design these spaces at this point is to look at that RARP methodology that's offered in table 8.3 and design towards that. And really, that still over ventilates the large room. Once you get up to a 200 or 300 square foot room, those code minimums are going to over ventilate. So if you have the opportunity to turn those down during off hours or unoccupied hours, then you should definitely do that. And here are some bullet points to say what I just said. So I'm not going to read those again. If you'd like to read this in white paper format, that is available. I think these get published in ASHRAE transactions, but it is a white paper format version of that. This is the reference for it. And I'm not sure how we're handling questions in the virtual conference, but please feel free to reach out and get a hold of me any way that you have the opportunity to do so.